In this lecture, we are going to study about functions. So, functions are one of the most widely used fields of mathematics. We will see. So, in our past few lectures, we were studying about relations. So, a function is just a kind of relation. So, it's a special type of relation. Remember, we used to denote our relation, some relation R from set A to set B. Some relation R. We will see that if although this is a relation, this is not a function. So we will see why it's so. So formally we say that a relation f from a set A to a set B, it's said to be a function if every element of set A has one and only one image in set Y. So for example, here we see that this image, some element here, it has two images here. So there is an arrow going from this element, suppose small a, to here B and C. So this element A has two images in B. So this is not a function. So although this is a relation, this is not a function. So every arrow, so from every element there can be only one outgoing arrow to second set. So then only we can say that it's a function, and this was our first condition. So we can write that our first condition was that relation f from set A to set B is said to be function if for every element of set A has one and exactly one image in set B. So one and exactly one. So even if some element here has, so here this has two images, but this has one image, but some elements are left out, like it does not have any image here. So it has basically zero images in this set. This has one image. This, suppose this is A prime. So this has one image in B, set B. This has two images in set B, and this element, suppose A double prime. This has no image in set B. So it should have one and exactly one. So I had said that this has two images, that's why it's not a function. But this also has a number other than one. It has no images, it's zero. So this point itself says that every element in A should have one image. So even if some element is left out, even if we have some example like this, where all elements had exactly one image here, but one element was left out, then also this is not a function, because this element has no image in B and it should have one and exactly one. So I will take one concrete example. and here we have 5 and 6. So suppose this is our relation from set A to B. So we will write this relation as 1 5 1 6. Clearly this is not a function. I am just writing the example of relation. So 2 5 2 6 and 3 6. So the domain of F. So here I said that every element of this A should have one image and exactly one image in B. So every element of A will have some image, so no element will be left out. So domain of domain of F will be equal to A, because in domain we write all the first elements of the pairs, and for all elements in A we have one element in B. Then all of these elements of A will form the first element of ordered pairs we write for the relation F. So the domain of F should be simply A, and no two distinct ordered pairs in F have the same first element. So for example here, for this relation, we have, if we compare, we see that here 1 is the first element of this pair, and here also. So what does this denote? So there is an arrow from 1 to 5 and from 1 to 6. So for this case, if we have multiple arrows going from one element, then only one will form part of multiple pairs as first element. So for this case should not be there for R to be a function. So now we will look one diagram where F is a function and not just a relation. So if we have 1, 2, 3, and here we have 4, 5, 6, 7, and we have a relation like this. So is this a function? So here 1 has how many images? So 1 is mapped to 4, 2 is paired with 5, and 3 is also paired with 5. So these are the elements from set A. So how many images that does 1 have? 4. Sorry, 1, because 1 is paired with 4. From 2 also there is only one arrow going out. From 3 also there is only one arrow going out. Is there any element left in this set? No. So our definition is satisfied here. that each and every element of A has one and only one element in B. So this is a function. Now a function, we will denote it. So suppose this is the function, then we will denote it as f, some function f. So it does not need to be f, we could have written function g also. So f, and then first set, the domain set from A to B. So we will denote it as this, and this is just denoting that f is a function from A to B. But how this function is defined, we have to write if A, B belong to F, if A, B belong to F, then f of A is equal to B. So we will write something like this. So this AB will form the pairs of F, and B is basically defined as a function of F. B is calculated using this FA. So we can define this FA in many different ways. We will see this when we see more examples of functions. So here we call B as image of A under function F, and A we call as pre-image of B under F. Under some different function it may be different, but so suppose we are defined a function, then so this function will have a set of ordered pairs. So here the first element will be called the pre-image of second element under F, and the second element will be called the image of A under F. So we will see some practical examples of functions. So we have a relation R defined as xy such that y is equal to 2x and xy belong to natural numbers. So what is the domain, codomain, and range of relation R? So this is one question, and second is this relation a function? So I have taken this example from NCERT textbook. So first we will write the relation R. So x and y both belong to natural numbers. So it's an infinite set, n is an infinite set, and we are not given any other condition like it should be less than this or more than this. So we can write 1, and y is 2 times x. So the second element is 2 times the first element. So it will be 1, 2. Then our next natural number is 2. So y will be 4. then 3 6 4 8 and so on. So if we have some kth natural number, we will have 2k. So this is an infinite set. This relation is also an infinite set, but one point to note is that natural numbers are 1 2 3 4 5 6 7 8 and so on. So this second element in the pair is 2 times the first element. So it can never happen that the first element will have, so one cannot appear in two different pairs, because double of 1 is 2, and so one will form pair with just one element. So 1 2 3 and so on. So double of 1 is 2. It's not that double of 1 is some other number also. So there will be just single arrow from 1. So 1 will form part of one pair only as a first element. So clearly this will be a function. So for this, answer will be yes. And now we will find the domain, codomain and range of this relation. So what will be domain? Domain will be the set of the first element of each pair. So 1 2 3 4. So basically for every natural number we can find its double. So the entire natural number will come under domain, or we can write it simply n, the natural number. Now what's the range? So the range is the second element. So second element is 2 times first element. So it's the double of any natural numbers. So only the even numbers will form part of this. So it will be 2, 4, 6, 8, 10 and so on, or even numbers. And codomain, you remember this is n, this is also n. So here also we will have 1 2 3 4 5, but here the even numbers will be image of some element, but these 3 1 these will be left out. So the codomain is this entire set. So the codomain would be again natural numbers, all the natural numbers. And this relation is a function, because corresponding to every element here we have one element in this second set, one and only one element. Now we have two more types of function. We will see sometimes we are written real functions, and sometimes we will also see some real valued functions. So what's the difference between these two? Difference between real valued functions and real functions. So here for a double of any natural number is a natural number. So all the elements here were also natural numbers. So the definition for real valued function is that if the range, so here this was the range for the above example. So if this range is a real number, if this range belongs to real number or some subset of real numbers, Then we will call this real valued function. So for real valued function, range should be some subset of real number. So here the range was even numbers, and we had seen that real number comprises of all rational and irrational numbers. So it will include all the natural numbers, whole numbers, integers, everything. And for this, so domain and range. So a function which has either R or one of its subsets. So R here means real numbers. So like where n denotes natural numbers, here R denotes real numbers. So if R or one of its subsets, like this natural number is a subset of R, even numbers is also a subset of R. So either R or one of its subsets is the range of F, then we will call this as real valued functions. So uh, the value, so we calculate value corresponding to each element in the domain. So if this function is f of x is equal to 2x, so the value of 1 defined by this function is 2. Value of 2 defined using this function is 4, and so on. So these values lie in the range. So real valued functions means the functions which uh, give some real valued output. So the value that is calculated using this function is some real number. So this value is what the set of the values calculated using this function is the range of this function. So if range is real valued, so if range is a real number or a set of real number, then we will see that it's a real valued function because this function calculates real values. And a real function is the function where both domain and range both should be from some subset of R or real numbers. So this is the difference between real valued function and real functions. So here, for example, here if fx is defined as two x plus 5, and we are given the condition that x belong to n. So here x is a natural number, so 2 times x plus 5 will also be a natural number. So this will also belong to n. So here the domain as well as range both belong to n, and n is clearly a subset of real numbers. So this will be both, this is both a real valued function as well as real function. So now we will take some examples of functions. So a function f is defined from real number to real number by y is equal to f x is equal to x square. So fx is defined as x square, where x is a real number, or that is x belongs to R. Then what is the domain range of this function? Draw graph of f. So if x is a real number, then so what will be x? F. So f will be clearly, so we take any real number like 0.5, then it will be square of 0.5, that is 0.25. So this forms a pair. If we take 3, then it will be 9. So for any real number we can find its square. So that is all the real number, uh, for all the real number we can find its square. So the entire real number, the entire set of real numbers will form the domain. So the domain will be x such that x belongs to R, and range is equal to all the x square such that x belongs to R. And now we have to draw the graph of this f. So first we will draw a table, or so if we are asked to draw a graph, then we will draw two axes, and the horizontal we will call as x-axis, and the vertical we will call it y-axis. And we will write here 1, 2, 3, 4, 5, 6. And on vertical axis also 1, 2, 3, 4, 5, and -1, -2, -3, -4, -5. So to plot we have to find y. So on this axis we will plot fx, which we have defined as x square, and on this axis we will plot x. So if we take 1 here, so here we have x and here we have y is equal to fx. On y-axis we will plot fx. So square of 1 is 1. If we have 2, then 4, 3, then 9, 0, then 0, -1, then 1, minus 2, 4, minus 3, 9, and so on. So, so 1 is 1. So this point will be here, 1, 1. Then for 2 we have 4. 1, 2, 3, 4 here. For 3 we have 9. So 4 is here, 8, 9. 9 would be somewhere here. For minus 1 also 1. For minus 2 also 4. And for minus 3, 9. For 4 it would be 16, way above here. So we will join these points. So for 0 we have 0. So it should pass from origin. So it will be more like this. So this is the graph of function fx equal to x square. So similarly, instead of x square, we were given y is equal to x cube, where x is a real number. Then how would we find? How would we draw the graph of this function? So again, we will draw the table. So here we have x and here we have y, which is equal to fx, and fx is equal to x square, x cube. So we will form the table, take some values. So 0, cube of 0 is 0, 1, 1, 2, 8. So here for either for positive number or negative number, we will always, the square is always positive number. So we had no value below this x-axis. All the values were above this x-axis because this uh, this is positive y-axis, and downward we have negative y-axis. So if some value is negative, it will come below this x-axis. But for the cube, for negative numbers, the cube will be negative because square is positive. Then again I multiply that negative number, so it will become negative. So for 3 it will be 27. Now we will take some negative values. For minus 1 it's minus 1. For minus 2 it's minus 8. For minus 3 it's minus 27. So now we can plot it. So this is origin, this is so this is suppose 2, this is 4, this is 6, and here we will have 1, 3, 5, minus 2, minus 4, minus 6, and so on. So this axis is x and this axis is y. So here we are plotting y equal to fx and x is equal to x cube. and then we have 2, 4, 6, 8, 10, and here we have -2, -4, -6, and so on. So for 0 we have 0. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 8 here. So it will come here. And for 3 it's 27. We cannot plot it. It will be far to the top. Now I take some negative value. For -1 it's -1. For -2 it's -8. So it will come here. And for -3 it will be some value way below here. So now I will connect these. So this is the graph of y equal to x cube, and this y is same as fx. So this was the graph of x square, y equal to f square, and this is the graph of y equal to x cube. Now suppose we have a function f defined from real number -0. So all the real numbers excluding 0 to real numbers defined by f(x) is equal to 1 over x. So x belongs to R minus 0, because if x is 0 then this value is not defined, so x can take any value from real numbers excluding 0. So now we have to draw the graph of this. So again I will write x, and here I will write y is equal to fx is equal to 1 over x. So for 1 it's 1, for 2 it's 1 over 2 or 0.5. For 3 it's 1 over 3 or 0.33. For 4 it will be 0.25. For 5 it would be 0.2. And now I will take some negative numbers. So -1 it's -1, -1 over 1 is -1, -2 then -1 over 2, that is -0.5, -3 it's -0.33, and now we will take some value between 0 and 1, because if we draw the graph here, this is x, this is y, this is 1, 2, 3, 4, 5 and so on. So first let me plot this. So for 1 it's 1, 2 it's 0.5, so 0.5 will be somewhere here. For 3 it's 0.33, so it will be somewhere around here. 0.25, 0.2, for 6 it will be even smaller. So we get a graph like this, which is slowly becoming near to this x-axis. And for minus 1 it's minus 1, for minus 2 it's minus 0.5, so for minus 3 it's, sorry, it will be here. So for minus 1 it's minus 1, for minus 2 it's minus 0.5, for minus 3 it's minus 0.33, for minus 4 it's minus 0.25 and so on. So here also this is like this. And now we cannot take 0 because at 0 it will be not defined, but we have to take value between this 0 and 1 and this minus 0 and minus 0.1. So let's take some values. So if it's 0.5, then it's 2. If it's 0.33, then it's nearly 3. If it's 0.2, then it's 5. That is, it's coming from 1 over, because this is 1 over x, so 1 over 0.2 is 5. And if it's 0.1, then y is 10. If it's even smaller, 0.05, it's 20. Similarly for negative values, minus 0.1, it's minus 10, minus 0.5, it's minus 2. So now we will plot these negative and these values between minus 1 and 1. So for 0.5 it's 2. So 0.5 will be here, it's 2 here. For 0.33 it's 3. For 0.2 it's 5. So somewhere here. And for 0.1 it's 10. Similarly for negative values, minus 0.5 it's minus 2. For minus 0.2 it will be somewhere here. It will be 5, that is here. So we join this. So this is the graph for fx equal to 1 over x, and you see that if we it's not defined at 0, but if we go slightly very small number right to the 0, it's close to infinity, it's a very large value. And if we go slightly to the left of this 0, we get a very large negative value. So just to the right of 0, it's plus infinity, close to plus infinity, and just to the negative of 0, it's minus infinity. So it's not defined at 0, and this would be the graph for fx equal to 1 over x. So if you are asked to draw the graph of any function, it's always good to first write a table, and these x values plot on the x-axis, horizontal axis, and this y values or the function, the defined function, we will plot on the y-axis. So that's it for now. In the next in the next lecture, we will see some predefined functions in maths, and we will see some more examples of function. So thanks for watching.